Okay, we're back. We have learned about related rates, and now it's time to do some homework problems. I assigned 4 problems, 17, 19, 23, 33. Hopefully these problems are not that hard, so let me try to do them kind of fast. Let's go. 17 says, I read from the book, the included angle of the two sides of constant equal length S of an isosceles triangle is theta. Okay, so whatever, yeah, I have some isosceles triangle, and these two angles are, or these two sides are S. They're, in fact, this problem, I don't want to say cheated, but it's this, I feel like this is a bad picture or something. Yeah, no, ugh. Let me just draw it the normal way. Isosceles triangle. I will just draw you like that. Okay, so here's some angle, and here's S, and here's S. What did they say again? The included angle of two sides of constant equal length S of an isosceles triangle is theta. Notice how they have baited you a little bit by suggesting variables for you and sort of telling you, hey, these are the quantities which are going to be changing. Hint, hint. Let the sides of equal length be S and let the angle between them be theta. Okay, there it is. I have read the problem and I have drawn a picture. Show that the area of the triangle is given by A equals 1/2 S squared sine theta. Okay, so this is now just pure pre-calculus. Part A says, yo, in case you forgot, there's a formula for the area of a triangle in terms of its side length and included angle, so just like do that. So how do you do this? You guys did this last year, but okay, I can just do it again. If you want to know the area of a triangle, you just drop a perpendicular, and now this is a right triangle, and the hypotenuse of this triangle is S. So this red altitude here is S times sine theta, because sine theta is that over that. Or just think of it as a, well, that's good enough. Okay, so what is the area of this triangle? Well, it's just 1/2 base times height. And the base of the triangle is S, and the height of the triangle is S sine theta. And so the base is S, and the height is S sine theta. And so indeed, the area of any triangle, or the area of any isosceles triangle is 1/2 S squared sine theta. Okay, and just more generally, the area of any triangle is just 1/2 AB sine theta, where theta is the angle between sides A and B. Okay, good. They just wanted to make sure that you knew that. Now we get to the real question, B. If theta is increasing at the rate of 1/2 radian per minute, find the rates of change of the area when theta equals pi over 6 and theta equals pi over 3. Okay, it's for this reason that I sort of do want to draw the triangle in a kind of a standard position, because I would like to think of the angle as growing over time. So let me just try a little bit harder to draw. How hard could it be? An isosceles triangle, sure. There it is. So that's theta, and those are supposed to be equal. Good enough-ish. For some reason it's hard to do from this angle. Okay, good. We're on part B now, and here's the triangle, so great. And sorry, what was the question? If theta is increasing at the rate of 1/2 radian per minute. In other words, what they're telling you is that d theta dt is 1/2 of a radian per minute. Okay, great. And find the rates of change of the area when theta equals pi over 6 and pi over 3. And so what they want are the two questions answered. What is the rate of change of the area with respect to time, specifically at theta equals pi over 6 and theta equals pi over 3. Okay, so read and understand the problem. There's not that much to understand here. Draw a picture. Okay, check. pick variables for the quantities which are changing. Here there's 3 things which are changing. 2 things which are changing because s is a constant. And actually that's important to keep in mind. S is not changing. S is just a letter representing the length of the sides of the bases, length of the sides of the legs of this isosceles triangle. What is changing? Theta is changing and the area is changing. That's it. Theta and the area. Okay. Pick variables for those quantities. They sort of did that already. Add those variables to your picture. Restate the information given in the problem in terms of those variables. Done. Now we just have to find the static relationship between those variables. So what is the static relationship between theta and a? Well, that's just the formula that they had us derive in part 1. So just like fact, a equals 1/2 s squared sine theta. Keeping in mind, once again, that s is not a variable, s is a constant. And okay, this is the relationship between a and theta. You give me a theta, I can tell you what a is. You give me an a, I can tell you what theta is. And now to find the relationships between the rate at which these variables are changing, then I take the derivative of both sides with respect to time. So on the left I get dA dt, and on the right I get 1/2 s squared. Again, s is a constant, so 1/2 s squared is just the coefficient. And I'm differentiating with respect to time. What's the derivative of sine theta with respect to time? Theta is something which depends on time, because theta is changing with time. And so I have to do the chain rule. So the derivative with respect to t of sine theta is, well, the derivative of sine of something is cosine something back inside for the derivative of the something. And in basically one step, I have found the relationship between the rate of change of A and the rate of change of theta. Okay, now let's just answer the 2 questions. So what is dA dt? When specifically theta is pi over 6, I think they asked for first. Well, it's going to be 1/2 s squared times, what's cosine of pi over 6? It's root 3 over 2. And was that what they asked first? And what's d theta dt? That's, for this problem, is just 1/2. And so the answer is root 3 over 8 s squared. That doesn't strike me as familiar, but seems fine. It makes sense that the area will be a function of s, because if the triangle is very large, then that's going to have an effect on how fast the area is changing. But anyway, there it is. Okay, and the second question is, what is dA dt at theta equals pi over 3? And I think it ends up being, well, I don't know. Let me not try to guess. Yeah, I get 1/2 s squared times, cosine, I'm using this formula again, of pi over 3 is 1/2, so I get 1/2 times 1/2, and that is, so it is different. It's 1/8, 1/8 s squared, and I guess the units would be whatever, like square units per minute or something like that. Okay, there it is. Explain why, now part C is just write a sentence. Explain why the rate of change of the area of the triangle is not constant, even though d theta dt is constant. Well, I don't know exactly what they want you to write here, but to me, it does make sense that as the theta is getting bigger and bigger, going from a very tiny triangle to a much kind of bigger triangle, that the rate at which the triangle is gaining area is not constant. Actually, if you want to do this, you can just draw back in this perpendicular, which has height s sine theta, of course, s times sine theta, and you can realize that as theta is increasing, the area of the triangle is just 1/2 base height. Well, the base is always s, that's just a constant. So it's really only the change in the height which is affecting the change in the area. And the change in the height is sine theta. Well, as theta changes, sine theta is not changing at a constant rate, or even a linear rate. We know that sine is, well, sine theta is, that function is simply not a line, it's a curve. And so we should expect that if the height is changing sinusoidally, it's just the definition of sine theta actually, it's just the height on the unit circle, then the area, which is a function of that height, the area of the triangle, which is a function of that height, should not be changing at a constant rate, but should be changing at a variable rate. And, well, then it also kind of makes sense what the answer is because, well, I'll stop there. Okay, one problem down, 3 to go. 19, I usually don't even go over this problem, so I think that means it's pretty straightforward, or at least I hope so. 19 says it's a problem about volume. It says there's a hemispherical water tank with radius 6 meters. Maybe this is not so hard, not so easy. So there's a hemisphere, so there's a tank in the shape of a hemisphere. The radius of the tank is 6 meters. It is filled to a depth of h meters. And so here's the fact is that h represents the height of the water in the tank. And so this little blue thing here is h. Okay, hopefully that picture is decent enough. Question. The volume of the water in the tank. Okay, here's why I remember this problem being not that exciting. Because instead of forcing you to do some geometry, in fact, I don't think you know how to do this yet, it just comes right out of nowhere and just tells you, hey, trust me, the volume of the partially filled water in this hemispherical water tank is 1/3 pi h times 108 minus h squared. Okay, in about 2 months, you're going to be able to have the skills to be able to derive that formula. But for now, they just give you this formula out of nowhere as being the volume of the water. And now they just say, water is being pumped into the tank at the rate of 3 cubic meters per minute. Find the rate of change of the depth of the water when h is 2. Okay, so I guess why this problem arguably is not that hard is because there's only one variable, h, really, which is changing over time, and of course the volume is of water in the tank is also changing over time. But the relationship between the height and the volume is given to you, and so what's the other thing given in the problem is the rate at which the water is being pumped into the tank, and that is 3 cubic meters per minute. In other words, dV dt, the rate of change of the volume, if water is being pumped in at a certain rate, then that water is contributing to the growth of the volume. So the rate at which the volume is changing is 3 cubic meters per minute. So cubic meters per minute. And now what we want to know, so what the problem is requesting, is the rate of change of the depth of the water. So what is dH dt at, and once again, the real question is what's the formula in general for dH dt, but because these problems like to have answers, they're going to ask you for what the rate is at a particular moment. Find the rate of change of the depth of the water when h is 2. So what is dH dt when h is 2? Okay, and now we just do the problem. Before I do it, I'll just say quickly that this is sort of a very reasonable kind of thing going on here. Assuming you had done some background work to derive this formula for the volume as a function of h, of course, dV dt is the thing you are going to know, because it's sort of directly measurable the rate at which the volume is changing, because presumably you're pumping the water into the tank at some kind of rate. And so if you're pumping the water into the tank at a certain rate, then you know the rate at which the volume is changing. But the rate at which the height is changing is far more difficult to measure empirically. So instead of putting a ruler in the water and hitting a stopwatch every couple seconds and recording it, you can just calculate dH dt if you know dV dt. So that's sort of the beauty of related rates, is that this rate is calculable in terms of this rate. shows how the rates are related. Okay, so now just fast, we do the problem. How do we do the problem? We take the relationship between the variables and we differentiate with respect to time. Okay, so I think it's probably easier to write this by distributing that h through. So this is pi over 3 on the outside, but then this is 108h minus h cubed. And so this is just a polynomial. And so now I differentiate both sides with respect to t. Then on the left-hand side I get dv dt, but on the right-hand side I get, and now I just differentiate everything on the right-hand side. So it's pi over 3 times, what's the derivative of this polynomial? Well, it's 108 minus, oops, careful. The derivative of 108h is 108 dh dt minus, and the derivative of h cubed is 3h squared back inside dh dt. So I guess that was the better way to do it. Uh-oh, baby's crying. So this is does 3 go in there? Yeah. So I can take a 3 out. So this is pi over 3 times. If I take a 3 dh dt out of this, then I get, oh boy, what is that? 33 and another 3 is 36. Yeah, of course, 36 times 3. So this becomes 36 minus h squared. Let's just double check that really fast. 3, Okay, so, and then these 3's cancel. And so equals dv dt. All right, so the general formula for dh dt is going to be dv dt over time, dv dt, and then I guess just like divided by pi times 36 minus h squared. Okay, so that's the formula. And of course, I know for this particular problem that dv dt is 3. And so really this problem becomes 3 over pi 36 minus h squared. Okay, and I would like to stop there, but I do want to do the problem, and the problem says, well, don't give me the formula for dh dt in general as a function of h. Give me the particular value of dh dt at the moment when h is 2. And so for that, I just plug 2 in for h. So that's 4, 32. So I guess I get 3 over 32 pi. And the units are meters per minute. Okay, so maybe that wasn't that easy. Okay, 2 more problems. 2 more problems, let's go. Okay, and I think maybe they're both a little tricky. 23 was hopefully not that hard because it was almost exactly like the problem that we did in the video, but it is maybe a hard problem. So here we go. Here's what it says. At a sand and gravel plant, sand is falling off a conveyor and onto a conical pile at the rate of 10 cubic feet per minute. Oh boy. Okay, so we have some, here's like the ground, here's some kind of conveyor belt, and falling off this conveyor belt or whatever is a bunch of sand. And the sand, for whatever kind of physics reasons, falls in such a way that it makes a cone of gravel. So here is the kind of cone of gravel. And maybe now I'll just erase the ground, because I think we get it. Or maybe I'll do like this or something. Okay, art skills, woo! Okay, so, at a sand and gravel plant, sand is falling off a conveyor and onto a conical pile at a rate of 10 cubic feet per minute. So we know, once again, the rate at which the sand is falling, which is kind of reasonable. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? Okay, I think I've made a typical bad mistake here, which is that my picture is too small. Let me just make a much bigger picture. And before I do it, the diameter is approximately 3 times the altitude. Okay, so for the particular type of sand under discussion, the gravity and stuff like that is going to give you a cone with particular dimensions. And the particular dimensions of the cone are that the diameter of the cone is going to be 3 times the altitude. So that perhaps looks right. Let me just try one more time. Oh man. The diameter of the cone is 3 times the altitude. So that this is the diameter, and then this is the altitude of the cone. That's what we're given. Okay. At what rate is the height of the pile changing when the pile is 15 feet high? Okay, so what's going on here? Sand is falling, it's making a conical pile on the ground, and the cone, the dimensions of the cone, or the shape of the cone rather, is sort of being given to you in advance. That the diameter is 3 times, I'll even just write that, the diameter equals 3 times the altitude. Okay, so I think I will pick so pick some variables now. Well, one variable to pick is the height of the cone, and perhaps we'll just call that h. So let h be the height of the cone. Well, if h is the height of the cone, then what is the diameter of the cone? Well, they told us directly in the problem that the diameter of the base of the cone is going to be 3 times as big as the height of the cone. So that makes the diameter of this cone 3h. Okay, and I guess it's up to you whether you want to think of this as like a separate variable or not, which is the radius of the cone. You can label that r, but almost immediately you're going to realize that r is just 3/2 h. So over here I'll just write 3/2 h because the diameter is 3h, so the radius is half of that. Okay, alright, now we can mention what is it that we are sort of given in the problem, or what is it that we know? What we know is sand is falling on a conveyor and onto a conical pile at a rate of 10 cubic feet per minute. And so that means that the volume is changing at a rate of 10 cubic feet per minute. And what we want to know is the rate of the height of the pile. At what rate is the height of the pile changing when the pile is 15 feet high? So what is dh dt when h is 15 is what we want. Okay, so read and understand the problem. There's not that much to understand. Sand is falling down, it's forming a cone of a particular shape. Read and understand the problem, draw a picture, pick variables for the quantities which are changing. In this case, the thing that's changing is h, the height of the cone. The radius is, of course, changing as the cone gets bigger and bigger, and the volume of the cone is changing. Restate the information given in the problem in terms of those variables. I know dv dt, and what I want is dh dt at a particular moment. And now find the relationship between the variables. Well, the relationship between the variables, if I think of myself as having 3 variables, the volume, the radius, and the height, perhaps that's the most honest way to do it, all 3 of those are changing over time. What is the relationship between those 3 variables? Well, the relationship between the volume and the radius and the height is just the formula for the volume of a cone. And the formula for the volume of a cone is 1/3 pi r squared h. But I don't really have 3 variables here. I really have just 2 variables because we have already determined that r is just 3/2 h, because r is just half the diameter, and the diameter is 3 times the altitude. Okay, so that means that the real relationship, or the simplified relationship between v, r, and h is that this is like pi over 3 times, in place of r squared, I'll just put 3/2 h, quantity squared. And now what I have is a single relationship, which will tell me the volume, the relationship between the volume and the height. Okay, so cleaning this up a little bit, that's just 9, so that becomes 3 pi over 4 h cubed. Hopefully I did that right. Yeah. And, well, that's it, right? Now, this tells me the relationship between v and h. I differentiate both sides with respect to t. So I get dv dt on the left, and over here I get 3 pi over 4 times the derivative of h cubed with respect to t is 3h squared back inside dh dt. And what do I want? I want dh dt. So what is dh dt in general? It's going to be 4 dv dt over 9 pi h squared. That's the general formula, but the formula given this particular rate at which the volume is changing, if that's 10, then this is really 40 over 9 pi h squared. And once again, I could stop there, but the problem asks for dh dt when h is 15, so now I just plug in 15 for h, and I get whatever I get. 15 squared is just big number, man, right? 40 over, I don't think anything cancels there. No, it does. This is 8 times 5, and down here is a 9 pi, and then 15 squared is like 5 times 75 or something like that. No, why am I screwing this up? 3 times 15, so 5 times 45 is another way of writing 15 squared. Right? Yes, because it's 9 times 5 times 5. So the 5's cancel, and I get something like 8 over 45 times 9, which is, God, this sucks. What's 45 times 9? It's like 405? Ugh, 360 and 45, yeah, 405 pi. I'm going to actually check this in the back of the book, because I don't think I've ever done this problem in class before. Units are feet per minute. I hope the answer is 8 over 405 pi. If not, it means I've made some kind of, mistake, but hopefully it was not a deep one. Section 3, riveting video. This is number 23. Yeah, 8 over 405 pi. Okay, good. Woo. Okay, 3 down, 1 to go. This problem is the most exciting of all. It is about baseball. Here's what it says. The problem's called baseball. A baseball diamond has the shape of a square with sides 90 feet long. See figure. Okay, so assuming you never knew anything about baseball, now's your time to learn. I know almost nothing about baseball, but I do know how to do this problem. Okay, so here you have a baseball diamond, also known as square, and it is the shape of a square with the sides of 90 feet long. Okay, see figure. And now, a player running from second base to third base at a speed of 28 feet per second is 30 feet from third base. Okay. So first of all, this is second base. This is third base here. So I mean, if you really know nothing about baseball, you just like run around, man, counterclockwise the various bases and try not to get tagged. At what rate is the player's distance s from home plate changing? A player running from second base to third base is... Okay, so this is very exciting. Oh, and then this is home. Okay, so what we have is there's a player on second base, and they are running from second base to third base. And then when you get to third base, you can just like stop and chill, or you could just like keep running and go back to home. Keep on running and go home, and then you like score, run. All right, well, where is this person? This person is running somewhere between second and third base. And where are they? Well, we seem to be interested in what's happening when the player is 30 feet from third base. Okay, so I'm going to draw this player kind of like over here or something, on their way this way between second base and third base. The question is, the person is running at 28 feet per second. Okay, so the person is running at a constant rate between second base and third base. The sides of this square are 90, let's not forget. And the question is, at what rate is the player's distance s from home plate changing? Okay, so now added to this problem is another thing that you might think is unexpected, which is how far is this player from home base? And they're suggesting that we call that quantity s. So I'll follow that suggestion and I'll draw in this purple line and I'll label this s. And of course this is a square, so this is a right triangle. And the question is, how fast is this player's distance from home plate changing? And okay, what I kind of find slightly interesting about baseball is, like, you know, this is basically a pretty much boring sport, but there's like a lot of kind of math going on, because at any given moment, like when there's some action that happens, like once every half an hour, you have to make these split-second decisions of like which player to try to get out first if you're on defense. And so there might be like multiple players all running at the same time to different places, and they're in different positions and they're running at different speeds. And if you are like the catcher, for example, and you have the ball, and perhaps there's a shortstop, that's like a position, which is running alongside this runner so that the shortstop can like tag the runner out, then the catcher needs to make a split-second decision, which is, how far away am I at this moment from the runner? How fast can I throw the ball? How fast is this runner running? How fast is the distance between me and the runner changing? And to calculate whether it's possible for the catcher to throw the ball to the shortstop lurking nearby to tag the runner out, or is it perhaps best for the catcher to just hold on to the ball or attack some different runner or something like that? Okay, so that's what's going on. I have this player, he's running from second base to third base. I know how fast he's running. Perhaps you can think of the baseball as being in the hand of the catcher, and thus S really represents the distance of the runner to the catcher. And the question is, how fast is that distance changing? And if you were going to like program robots to play baseball, then you would probably teach them calculus, and you would tell them to perform all these calculations and to decide what to do with the ball based on all of the rates at which these distances are changing from each other, from the person with the ball to all the various runners and people on the same team. Okay, so read and understand the problem. Check. Pick variables for the quantities which are changing. Well, what quantities are changing? I say that two things are changing. The distance the runner is from home, but also the distance the runner is from third base. So this is, I'm going to call this x, because why not? X is the distance of the runner from third base.